Efficiency for 3D compression. As mentioned above, the compression of multi-channel RS images can be carried out component-wise in using variance of 3D approach. In the former case, there are certain benefits. First, it is easier to handle data. For example, QS or BPP can be set individually for each component image. Second, a part of operations can be performed in parallel. For example, orthogonal transforms and quantization of coefficients can be performed separately for each component image and, thus, this part of processing can be parallelized. In the latter case, 3D compression can be applied to multi-channel image as a whole or as to a set of component image groups. Each variant has its own positive features and drawbacks. If groups are used, it is easier to parallelize computations, since processing can be partly performed separately in each group, and adjust compression parameters. Noise-free, A, and noisy, B, 3-channel test image in pseudo-color representation. Let us analyze some peculiarities of 3D compression for a rather simple 3-channel test image, presented in A. This image has been considered noise-free and it has been composed from 3 channels of visible range of Landsat RS data associated with red, green, and blue components for visualization. The noisy image with artificially added AWGN having the same variance equal to 130 in all components is shown in B. Noise is seen well in quasi-homogeneous regions. The plots of MS at QS are presented in A. Notation 2D relates to two-dimensional, i.e., component-wise compression. For all 3 components, the plots almost coincide and, therefore, we present the average dependence. In turn, notation 3D concerns 3D compression using 3D version of AWGN coder. Again, the dependence averaged for all 3 components is given. There are several interesting observations for these plots. If QS is rather small, for example, less than 2 sigma, the dependences MS at QS practically coincide, i.e., there is almost no difference between 2D, component-wise, and 3D, volumetric, compression. Then, for larger QS, differences start to appear. And they become quite large for QS about 4 sigma, i.e., when OOP can be observed. First, OOP is observed, CA, for both 2D and 3D compression. But MS at QS in OOP for 3D compression is considerably, by almost 2 times, smaller. This means that noise filtering effect due to 3D compression is sufficiently better compared to 2D compression. This can be noticed in that presence images compressed in OOP for 2D and 3D AWGN coder versions. Second, OOP in the case of 3D compression is observed for the same conditions as for 2D compression. More examples confirming this can be found in the paper. Average dependences MSEC QSI and for QSB for 2D and 3D compression. Images compressed in OOP for 2D, A, and 3D, B, compression. Consider now the plots of CRQS represented in B. For QS less than 2 sigma there are almost no benefits of 3D compression. However, for larger QS, the benefits become obvious. CR provided by 3D compression occurs to be almost twice larger than for component-wise processing. A question is why this happens. Another question is, can we predict CR in situations when 3D compression might be beneficial compared to component-wise coding? There are 2 main compression parameters for which prediction is desirable for compression in OOP neighborhood, namely, delta snrCoop and CR. An approach to predict delta snrCoop for component-wise compression has been recently proposed. Its essence is the following. Suppose that one has a parameter that is able to jointly characterize complexity of image to be compressed and noise intensity in it. Suppose also that this input parameter can be calculated easily, quickly, considerably faster than compression is performed, and it is tightly connected to output, predicted, parameter, indicator, that characterizes compression from a desired viewpoint. This connection is expressed either as some analytical dependence allowing to determine, predict, output parameter easily and quickly. Then, it becomes possible to estimate the input parameter for a considered image, to use it as argument for calculating the output parameter, and to carry out some decision based on this prediction. Having described the general strategy of prediction, let us give some details. First of all, there are many parameters that can be used as inputs. Under condition that noise parameters, variance, are known in advance or preestimated with appropriate accuracy. Statistical parameters of the family P alpha sigma can be used. These are mean probabilities that absolute values of DCT coefficients calculated in blocks of size 8 times 8 pixels are less than a threshold alpha sigma where alpha is the parameter. In our experiments it has been equal to 0.5, 1.0, 1.5, or 2.0. The input parameter P alpha sigma is indirectly connected with number of zero DCT coefficients in image filtering that influences denoising efficiency performed by lossy compression applied to noisy images. There is also parameter P0Q mean probability that DCT coefficients calculated in blocks of size 8 times 8 pixels are equal to 0 after quantization with a used QS. Obtaining dependence between output and input parameters is a special stage performed in advance, offline. This stage presumes getting a scatterplot where the horizontal axis corresponds to an input parameter and vertical relates to a predicted output parameter. Scatterplot points correspond to a test image corrupted by AWGN with a certain variance compressed in a specified way. An example of the scatterplot is shown in P2 sigma serves as an input parameter and delta snoop as an output parameter. Having such a scatterplot, curve fitting is applied to obtain a desired dependence. At this substage, several subtasks should be solved. They can be, in general, treated as providing good fit and include choice of proper type and parameters of approximating functions, accounting for restrictions, etc. Different criteria of fitting quality can be used where R2, goodness of fit that has to approach unity for good fit, is one of the commonly employed parameters. The example for 2D image compression presented in shows that the scatterplot points are not spread a lot and it can be assumed that the dependence is a smooth function. Then, polynomials of the fourth and fifth orders and some other functions provide appropriate results. The fitted polynomial expression is presented in. The performance of prediction for different input parameters should be analyzed and compared since considerably different values of R2 can be potentially and practically produced. Some analysis has been already carried out but this study is far from completeness. Scatterplot of delta snoop pump 2 sigma and the fitted fourth order polynomial. Scatterplots of CR vs B1 sigma, A, and 0 QB and the fitted curves. Similar strategy has been applied in the prediction of CR for 2D compression. The first attempt to predict CR for lossy compression of noisy images in UP for AGU and ADCT coders has been made in 2015 using two input parameters, P2 sigma and P2.7 sigma. A more thorough study has been carried out later. Below we present two scatterplots from the aforementioned paper. As it can be seen, both scatterplots have small spread and, according to their visual inspection, CR has the tendency to increase if the input parameters P1 sigma or P0 Q, considered here as example, become larger. Fitting is excellent in both cases although the results for P0 Q are slightly better. Here, tight connection of CR with P0 Q is easily understood. A larger P0 Q shows that there are more zeros in a sequence to be coded and this in turn leads to a larger CR. Dependence P0 can QS for 2D and 3D compression. Thus, we can expect that benefits of 3D compression compared to 2D deal with more zeros after 3D DCT, better decorrelation of the data, than in component-wise compression. To check this hypothesis, we have determined P0Q for 3D compression and for 2D component-wise compression for the test image N, B. The results are given as dependencies of P0Q on QS for 3D AGU, notation 3D, and for two components, red and green, notations 2DR and 2DG, respectively. As it can be seen, the curves for red and green channels practically coincide. In 3D compression, more zeros are observed for any QS. For optimal QS equals 56 one has P0Q about 0.87, the predicted CR is about 13, CB, and this practically coincides with the value of practically attained CR, B. In turn, for 3D compression, P0Q is about 0.92, the predicted CR is over 20, CB, and this is in good agreement with the value of practically attained CR, B. Certainly, a more thorough study is needed. However, we can expect that the prediction of CR using P0Q can work for 3D DCT based compression as well. The observations described above have also been verified for two types of multichannel images. The first type is Landsat TM data. Different variants of uniting 8 images of the same resolution into groups for further 3D compression have been considered. It has been shown that there are benefits in CR. It sufficiently increases for the same level of introduced distortions, only if images combined into a group are highly correlated and have similar dynamic range. Then, there is an increase in the percentage of zeros P0Q for 3D coder compared to P0Q for component images within this group. This increase can serve as an indicator of expedience to apply 3D compression.